All right, 5.2 here is split up into two different sections. There's a 5.2 study in 5.2.1, and then there's a quiz, and then there's another study portion, and then another quiz after that. So like that, like the Apex, I split mine up into two also. So you can see when you look at your study guide that I split it up so you can follow along. 5.2.1 is what we're covering in this video. It should correspond directly to the 5.2.1 study section in Apex. After you complete this video, you should be ready to do the first quiz. Then come back to watch the 5.2.4 study portion. So in this section, this is pretty much just a whole lot of vocabulary. And you basically just want to make sure that you have these definitions filled in correctly and you have a pretty good grasp of what these words mean. In the next part of this section, in the next video, we'll go over how we can actually find probabilities of these different things based on how things are related. So basic vocabulary of probability. So the first thing here, a random experiment which is also called a probability experiment sometimes, is an experiment where we're applying a treatment just for the purpose of observing outcomes. So think like rolling a die, pulling a card from a deck, pulling a marble from a bag, pulling a name from a hat. All of those things are random experiments. All we're doing is trying to observe the outcomes, and generally this is what we do when we're trying to predict probability of something happening. Every time when I'm performing a random experiment, each time that I do something, like if I roll a die or I pick a card or I grab something from a hat, each time that I do that, I am performing a trial. A trial is a single action leading to a single outcome. So if I roll my die 10 times, then I'm performing 10 trials in a random experiment. An outcome is a single possible result of a random experiment, a member of the sample space. The sample space is all the possible outcomes that we can get. So within all the possible outcomes that we can get, each single outcome is a single possible result from our random experiment. So again, if we're rolling a die 10 times, we have 10 trials with 6 possible outcomes because there's only 6 sides to the die. Another example they give here, they say flipping a coin has 2 possible outcomes, heads or tails. Flipping 2 coins together yields 4 possible outcomes. We could have 2 heads, heads then tails, tails then heads, or 2 tails. So if I flip 2 coins 12 times, that's 12 trials, but I still only have 4 possible outcomes in my sample space. An event is an outcome, or it could be a combination of outcomes. From a random experiment, also known as a subset of the sample space. So, for example, if you flip 2 coins, then we know the sample space again is this here we saw above. The event, 1 head, can occur in 2 ways. We could get heads first, then tails, or tails first, then heads. So the event having 1 head has 2 possible outcomes out of 4 in the sample space. A simple event is an event that only includes 1 element. So if a simple event is an event that only has 1 outcome in the sample space that satisfies that. So for example, in the coin sample space, the heads heads and the heads tails and the tails heads and the tails tails, that was our sample space, the event 2 tails only happens once. Therefore, the event 2 tails is called a simple event. So when we're calculating probabilities, we're actually calculating probabilities of an event. So an event can be 1 outcome, or it can be multiple outcomes, and an outcome can have more than 1 factor in it. The sample space, again, is a set of all possible outcomes, like the set of all possible outcomes we had in flipping a coin twice. The probability of an event is the number of ways an event occurs as a fraction of the total possible numbers of events. It's also known as the relative frequency of an event. We defined this one in the last section, so I'm not going to go over that again. We will see lots more examples of this though in the future. Okay, one thing that is new though here is this thing complement. The complement of an event is the event that something does not happen. So if A is an event, then the complement of the event, which we denote with this superscript little c there on it, is the event not A. Or in other words, it's the event that A does not occur. So we have an example here. It says the probability of A plus the probability of AC, not getting this example yet, sorry. The probability of A plus the probability of A's complement is always going to be equal to 1. Always, 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 all of our possible events that we look at in any probability experiment, their sum will always be 1. Think of it, if I add up all of the possible outcomes of a probability experiment, what's the total probability of any probability experiment? It has to be 100%, right? If I include all the outcomes, I better get 100%. If I add them all up and I get something less than 100%, then we definitely left out an outcome. So if I add the probability of an event happening to the probability of it not happening, then I have all the chances. So here's an example now. If B is the event, roll a 5 on a 6-sided die, then the complement of B, BC, is the event. Don't roll a 5 on a 6-sided die. Well, what would that mean? If I rolled a 6-sided die and I didn't get a 5, what did I get? Well, I got either a 1, a 2, a 3, a 4, or a 6. So what is the probability of B anyways? Well, the probability of rolling a 5 on a 6-sided die, well, there's only one 5 out of 6 numbers on a 6-sided die, so the probability of rolling a 5 is 1 out of 6. And what's the complement of that? Well, I could add up all of the possible outcomes that are not rolling a 5 and calculate probability that way. Or an easier way to do this, especially when we have lots of outcomes, is I can just take the total probability, 1, and subtract the probability that B does happen. We just found out the probability that B does happen was 1 out of 6. And 1 minus 1, 6 is 5/6. Notice if I were to do this the old-fashioned way, we get the same thing. What's the probability that I roll a 1, a 2, a 3, a 4, or a 6? That's 1, 2, 3, 4, 5 outcomes out of a possible 6 outcomes in our sample space. So anytime that you need to find the probability of a complement of an event, you just subtract the probability that it does happen from 1. And it works the other way around too. If you need to find the probability that something does happen, and it's easier to find the probability that something doesn't happen, find the probability that it doesn't happen, and then just subtract it from 1. The next topic here is mutually exclusive events, also called disjoint events. Disjoint events, or mutually exclusive events, are 2 events that, there we go, that never occur at the same time. So it is possible for 2 different events to occur at the same time, but if we're talking about mutually exclusive events, that means they're never going to occur at the same time. So the example they say here, the chosen card can be a 4 or a jack, but it can't be both at the same time. So these are mutually exclusive events. Alternatively, that card can be a black and a jack. It is possible for a card to be both black and jack. So the event of drawing a black card and the event of drawing a jack are not mutually exclusive. In order to be mutually exclusive, it has to be impossible for the 2 events to happen at the same time. Let's talk about another example. What if I'm rolling a die? If I want to roll an even number and I want to roll the number 2, those are not mutually exclusive because 2 is even. They can occur at the same time. But if I want to roll an odd number, and I have another event where I roll the number 2, those are mutually exclusive because they cannot happen at the same time. The next term here is dependent events. Two events are dependent if the occurrence of one event changes the probability that the other event occurs. So for example, it says, I see clouds above my head and it's raining. These are dependent events because if it's cloudy, it's more likely that you don't see clouds above your head. Oh, sorry, if it's cloudy, rain is more likely than if you don't see clouds above your head. Another example would be like if I'm at school, it's more likely to be a Wednesday than if I was not at school. Because if I am at school, that means it's definitely not a weekend. So there's only 5 possible days instead of 7. With an independent event, with 2 independent events, that means the probability that the fact that one event has occurred does not change the probability that the other events have occurred. So for example, imagine you're tossing a coin twice. Tossing a coin one time and I get heads, it's not going to affect what I get when I toss it the second time. And they say here also, let event A be getting tails in the first toss and B be getting tails in the second toss. Tossing a coin once has no effect in what the second toss is going to be. A different example would be like if I pull a card out of a deck and I look at it, maybe it's a 5 of spades, and then I put it back in the deck and shuffle it. When I pull a card out of the deck again, the probability of getting anything is no different than it was before because there's still the same 52 cards randomly inside the deck. However, if I take a card out and I don't put it back, I've automatically changed the probability of getting any type of card because the number of cards in the deck has been reduced by 1. So dependent events, I didn't put the card back. Independent events, I put the card back and the probabilities did not change. Another way that we can look at all of these types of events and how they're related is by using a Venn diagram. A Venn diagram is a graphical representation of how the different events, simple events, and outcomes included in a sample space are related. So the example they give us here, we have 2 different events, A and B, and you can see here that they're overlapping, which means they are not mutually exclusive or disjoint. If these two events were disjoint, then their Venn diagram would have absolutely no overlap. So let's go and look at solving some basic probability problems in this section. First thing, it says a 6-sided die is rolled twice. What is the sample space? So if I roll a 6-sided die, I could get a 1 the first time and a 1 the second time. Or I could get a 1 and then a 2. Or a 1 and then a 3. Or a 1 and then a 4. A 1 and a 5. Or a 1 and a 6. Or I could get a 2 and a 1, a 2 and a 2, a 2 and a 3, 2 and a 4, 2 and a 5, or a 2 and a 6. So there's my whole sample space. And notice I put the curly brackets around the outside. Curly brackets are the symbols that we use when we're indicating that something is a set. And a sample space is a sort of set. So now we can look at and find the probabilities using the sample space. This is one of the nice ways to find probabilities. If you have your sample space completely written out, it can be a lot easier to do these things. The first one, probability of rolling 2 6s. The only time I roll 2 6s is in this outcome down here. So the probability of rolling 2 6s, the probability of rolling 2 6s is 1 out of 12. Wait, no, not 12. Hold on. 36, of course, 36. Now, what's the probability of rolling at least 1 6? So that would be 1 6 or 2 6s. So I'm going to go through and highlight every instance where I see either 1 6 or 2 6s. So I see one here, here, here. We already have this one highlighted. All of these, this one, and I think I got them all. So how many did I highlight? I had 6 down here, 7, 8, 9, 10, 11. 11. So there are 11 outcomes that have a 6, either 1 or 2 6s, out of 36 again. Now it says 1 6-sided die is rolled. What is the sample space? So now that we're only rolling 1 die instead of 2, our sample space is going to look much different. I could roll a 1, a 2, a 3, a 4, a 5, or a 6. That's it. Those are all of my possible outcomes if I'm only rolling 1 die 1 time. So if I only roll 1 die 1 time, what is the probability of getting an even number or a multiple of 3? Well, here's an even number, here's an even number, here's an even number, and we have a multiple of 3 right there. So if I include everything that is either even or a multiple of 3, I see 1, 2, 3, 4 successes out of 6, which is the same as 2 out of 3. Next one, what's the probability of getting an even number and a multiple of 3? I'm going to rewrite my sample space here. It's not very long, so it's not hard to do. What's the probability of being an even number and a multiple of 3? So when I see the word and, that means I'm looking for outcomes, single outcomes that satisfy both of these conditions. So for instance, number 2 is even, but it's not a multiple of 3. So I'm not going to include that. I only want to include outcomes that satisfy both events. So which even numbers do I have here that are a multiple of 3? Just the number 6. The only other multiple of 3 I see here is the number 3, and number 3 is not even. There's only one outcome out of 6 outcomes that is both even and a multiple of 3, sorry. Okay, moving on. There are 5 red balls, 3 yellow balls in a bucket, and you pull out 2 randomly. Event A is that a yellow ball is drawn from the bucket first, and event B is that a yellow ball is drawn from the bucket second. Are these events independent? No. Think of it this way. What's the probability of A? The probability of A is, let's see, we have 3 yellow balls out of 8. If I take a ball out, though, what's the probability of B given that 1 yellow ball has already been taken out? Is it still 3 over 8? No, because now there's only 2 yellow balls in the bucket, and there's only 7 balls in the bucket total. So these are not independent events because the probability of drawing out a yellow ball the second time is not the same as the same probability as drawing a yellow ball in the first place. So now we're asked, what is the probability of drawing 2 yellow balls? To find the probability of drawing 2 yellow balls, I'm just going to multiply those other 2 probabilities together. The probability of A and B is going to be the probability of drawing 1 yellow ball times the probability of drawing a second yellow ball, given that we've already taken 1 out. So that's 3/8 times 2/7. And if you don't remember multiplying fractions, we just multiply across. 3 times 2 on the top gives us 6, and 8 times 7 on the bottom gives us 56. Which is the same thing as, let's see, 3 over 28. And the last thing, what is the probability of drawing at least 1 yellow ball? Well, for this one, let's go ahead and look at the whole sample space. Let's see, we could draw, when we're drawing 2 balls, we have, let's see, 5 red and 3 yellows. So I have yellow, 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 and 5 red, I said? Did I say red? 1, 2, 3, 4, 5. So how many different ways could I draw at least 1 yellow ball? Well, I could have 2 yellow balls, and notice these balls are independent of each other. So I can call this yellow 1, yellow 2, yellow 3, red 1, red 2, red 3, red 4, and red 5. So I could draw any combination of these 2 yellow balls. In fact, I think I did the last one wrong. I'm going to go back to that. If I want to draw 2 yellow balls, I could draw yellow 1 and yellow 2. I could draw yellow 2 and yellow 3, or I could draw yellow 1 and yellow 3. And I could draw them in the opposite order. Yellow 2, then yellow 1. Yellow 3, then yellow 2. And yellow 3, then yellow 1. There's actually 6 possible outcomes where I have actually 2 yellow balls. And how many total outcomes do I have here? Well, I have 1, 2, 3, 4, 5, 6, 7, 8 choices when I draw my first ball. And when I draw one out, there's only 7 left. So I have 7 choices for my second ball. So 8 times 7 is 56. And look at that, I get the exact same answer. 6 over 56 is still 3 over 23. So I did it right either way, actually. We're going to go back to the way I did it the first time, though, in the next section. So I was getting a little ahead of myself. So for now, let's go ahead and keep looking at just this sample space and kind of do this theoretically. Okay, we'll get to some more tricks on how to do this simpler in the next section, which is what I was trying to do. So what's the probability of drawing at least 1 yellow ball? We already know that we have 6 ways of drawing 2 yellow balls. So how many ways do I have then of drawing just 1 yellow ball? I could have yellow 1 with any number of these reds, so 1, 2, 3, 4, and 5, and I could have it in the opposite order. So that's 10 possibilities with yellow 1. Get a yellow 1, red 1, yellow 1, red 2, yellow 1, red 3, and so on. And then I could have it in the opposite order. Red 1, yellow 1, red 2, yellow 2, yellow 1, and so on. And the same thing I get for the other yellows. Yellow 2 has 10 possibilities of being chosen. And yellow 3 has 10 possibilities of being chosen, paired with each of the 5 reds in either order. That's 30 possibilities out of the 56 where 1 yellow is chosen, and then the 6 possibilities, 6 outcomes where both balls are yellow out of the 56. So that's 30 plus 6 is 36 successes out of 56 possible outcomes. Ooh, that's a lot. So that is, let's see, that simplifies to 18 out of 23. Yeah, 18 out of 23. So very high probability, actually.